So we started off this year with planning just our swerve bot. So we went through, made 3 or 4 different bots, or just the swerve frames, whether it was longer one way, shorter the other ways, just testing to see which layout we think would work the best. So we ultimately decided that we were going to go with a 29.5 inch by 29.5 inch square swerve bot this year. So we went in and made all of these uh, rails for the swerves, and we cut out weight reduction holes and as well as mounting holes on the top and on the sides, and then we copied that same pattern on the sides of the long ones that go through the middle for us to mount all of our superstructures on top of. And so we decided that our lift mechanism for our intake would be an elevator. And so we, in a separate file, modified the elevator to be shorter so that we would be under the weight cap, or under the weight, not weight, under the height maximum. So we had to cut down 15 inches from each of the stages. We had to cut down 15 inches, and then so we were going to make a pivoting arm in the middle of the elevator to be able to move our intake up and down. So we have a max planetary gearbox, 90-degree gearbox in here with a 9-to-1 and a 5-to-1 cartridge to be able to articulate the arm. And then we designed these custom plates to be able to hold the gearbox in place inside the carriage. And then we have our intake arm that is able to move up or down based on what we need, whether we're intaking or scoring. And then this is our intake design. So whenever it's in the intake format, it'll be down on the ground to intake the ball, and then we'll come up a little bit to be able to intake the coral, and then up some more, and then as well as rotating the arm up, rotating the angle of the arm up for the human player station, and then we're able to reach all the way up and articulate the arm upward to be able to score into the barge. And then for our scoring on the reef, we actually, instead of turning the robot around, we'll be rotating the arm all the way around and scoring with our intake upside down for L4, L3, L2, and L2. And then we'll have to score L1 with the intake back at that angle. And so we'll be able to traverse the field with everything fully protected while holding a coral, as demonstrated here. So we'll be able to hold a coral and the intake here, and then be able to go around the field. So this is really helpful with being able to plan out more things with our robot, whereas before we didn't really realize how big of the height difference would be for what the elevator came as versus what we needed to cut it down to. And so being able to model this in a 3D space made the visual representations of how long these pieces needed to be. So originally when we were assembling it, we got confused. We thought that the outward piece was supposed to be like the 34-inch piece, whereas the inside pieces were the 34-inch pieces. And then so that was a lot easier for us to be able to visually see that. And Also, with being able to 3D model all of these, we were able to cut all of these holes for ourselves without having to purchase these pieces of aluminum from the manufacturers, able to which allowed us to save a whole lot more money on this elevator. Um, being able to have this three-dimensional model of the carriage as well allows us. Let me move this real quick. Having the carriage allowed me to be able to design these motor mounts for the 90-degree gearboxes. So have some weight reduction up here, and then we left it solid down here so that if there's any forces that were applied to the arm, it would have more structure down here at the bottom where the mounting holes are. And so having the accuracy of the physical model in Fusion 360 made it a lot easier for us to be able to visualize what we needed to make. And then there's certain things like the weight reduction in this plate that we would never be able to do just by just hand drawing it and doing it with any hand tools. So being able to go in and draw this in Fusion and then actually adding it to the robot makes everything a whole lot easier, as well as being able to test things like the geometry of things. So let me put the arm in the scoring position, or in the intaking position rather. So then we're able to bring in the actual game pieces themselves. So originally we had the centers between the center wheels on the top and bottom was originally only 10 inches, and so this top wheel was moved to about where the outside edge of it is. And whenever we were testing it in like physically, and then also here, the bottom wheels were actually blocking the ball from actually being able to be uh, grabbed onto by the wheels. And so all we had to do was extend the length of this arm and then lower the angle down so that whenever the ball is on the ground, so bottom's equal with the bottom of the swerve wheels, this is the top wheel is actually the first wheel to come into contact with it. So it'll be rolling the ball towards the intake, as well as with the coral. If we have the intake at the same height as the algae, it would just slam into the wheels and it wouldn't be able to be grabbed onto. So we realized that our programmers were going to have to do 2 different presets for floor intakes so that the spear of our intake would be a lot higher. It's approximately 1.5 inches higher than what it was for, say, the algae. Because if it was here, the algae would not be able to be grabbed onto by this top wheel. So being able to have a three-dimensional model of these game pieces as well as our robot really allows for us to be able to kind of see how the geometry of things are going to be, and if we need to make any modifications to those, we can go ahead and do that before we cut it out in expensive materials.